Now let's go ahead and sketch a picture of this stress field. So we have the side view of this particular segment. Remember, it had 60 to the left, so therefore it must have 60 to the right. So that shows us the direction of tau. So by our right-hand rule, we know that it's going to go in the direction of our finger curl as we point our thumb to the right. So if we blow this end up, like so, we know that it is going to be going in this direction. So remember, our thumb is pointing that way, and so the finger curl goes this way. So that's going to be the value of 2.6 KSI. If I go up here, it's going this way. If I go to this side, it's down. If I go to this side, it's across like so. And then it's going to vary linearly. So the stress distribution is going to be linear as I move away from the center of the radial line. And remember, furthermore, this one is hollow, isn't it? So it's going to look like this. So it's going to look, if we blow it up even more, let's blow up this segment. And let's put the hollow section right here. So that means that this segment, if that is our center, that's going to be our value of 2.6. And the inner diameter is actually half that value. So this one's even easier to sketch. If we wanted to, we could calculate that that's going to be 1.3. So at a radius of 2.5, we have the shear stress of 2.6. And then at a radius of at 1.25, we have exactly half of that sketch. And that's the direction that they're going. So again, over here, it would be going this way, and this way. So that would be our field of arrows. And again, at this location, it's going this way, this way, this way. So we have a linear stress distribution all the way around that. And they integrate to give us a value of 60 that we have going in that direction. So that's a sketch then of what the field of arrows stress field looks like for this particular state. Furthermore, if we wanted to, notice we could take a little cut this way. We could take a little free body diagram out of that section and blow it up, and what would it look like? Then I would have over this slender segment, where again, this is our x direction. That's the direction of the axis. I would have a shear stress going down. Well, that means that we have a shear stress going this way and along the back face. Remember, heads and tails are together. So on the underside, it would go this way, and on the back face, it would be going like so. So that would be our element of our little segment of our cylinder in pure shear. We only have a value of 2.6, and it's going to be on all four faces for that particular segment. So once again, to re-emphasize, the tau follows t in terms of its direction or sign. So you don't really need to worry about plus or minus, but I do want you to consider the physical direction. So let's write that down. Note, don't worry about plus or minus, but I want you to focus on the physical direction. That I do want you to keep track of, and make sure that you realize that you are going to follow then the torque that we have. Well, since we're here, let's go ahead and calculate the rotation then. So once again, I'm going to redraw this. We have 60 going this way. That means that the theta is going to be this way. So the theta of B relative to A. Now, if we wanted to, we could also just call that theta of B, because A is not moving. So the absolute twist at B is the absolute twist of B relative to A. It doesn't make any difference because A is not moving at all. So it's going to be going in this direction. And for that, we could write the torque in A to B times the L of A to B divided by the J of A to B and the G of A to B. So TL over JG for that particular segment. And what's that going to be? That's going to be equal to the torque, which is 60. And let's switch it around now. Let's call it kip inches. And then we have the length. Remember, we've picked out units of inches, so that's going to be 24. Then the J, we already wrote that last time, but I'll do it again. Pi over 32 times 5 to the fourth minus 2.5 to the fourth. And then the G value that we've got here is 5,600 KSI. So remember, K. If our units of force are kips for the torque, they have to be KSI for the value of G. So we're not harping on that perhaps as much as we should, because a lot of students do make that mistake. But most people by this time, you know enough to watch for it, so just be wary. And if you get an answer that's off by a factor of 1,000, you've probably made some sort of units mistake. And what do we find? That's going to be equal to 0.00447 radians. And then we tell our reader that it's going that way. So that is the theta of B. Let's box that up. That is the rotation or the angle of twist at point B. And that's small, remember. If we want to get it in terms of degrees, we'd multiply it by 180 divided by pi, so roughly about 60. So that would be what, if we multiply it by 6, that'd be 0.024, so 0.24 degrees. So a quarter of a degree or so. Very, very small. All of our displacements in this class, our angles of twist, are going to be a small change in angle. Otherwise, we've got some problems. Now, we already did the statics for the next segment. So from B to C, remember we found that the torque, I'll rewrite it, the torque of BC is equal to negative 40. And we don't care about the sign for the shear stress, but we realize that it's going to give us then the physical direction from A to B is actually going to be this way. So 40 going like that. Remember, these two are equivalent. So this is the one that we would do just as a statics calculation. But if somebody said, what is the true physical direction of the torque? It's going to be going this way. So that's the one I want you to worry about. Don't worry plus or minus. I want you to get the physical sign of the shear stress. So in this case, again, we use tau is equal to T rho over J, but we're very careful to apply it for the torque in that particular segment. So I'm going to just put the magnitude of the torque, because we already know its physical direction. The value of rho then, remember this one had a diameter of 3.5 and it was solid. So 3.5 divided by 2 if we work in terms of the diameter. And then the value of J is pi over 32 times 3.5 to the fourth. And that gives us 4.75 KSI. And we notice immediately that that's larger than the max shear stress. And maybe I should have said max in segment BC to be consistent with what we did last time. And so for that, we would really be putting the value of the torque in the segment, and we would do the rho max. Remember, J doesn't change. J is the same for the cross section. But in this case, the rho would vary linearly, and so we get a value of 4.75. So immediately we can answer the question that was posed at the beginning of this example problem. That is the maximum shear stress anywhere in the entire segment is going to be this guy, because it's bigger than 2.6. So that would be 4.75 KSI. And we box that up so that our coworkers or our client or our boss can see what the answer is going to be. Now, what does this look like in pictures? We now know that the physical direction is the double arrow going to the left. So if I draw that now, going to the left, that means it's going to be going this way. Like so. And it varies linearly. So the size of the arrows goes down in linear fashion and eventually hits 0. So you've got 4.75 KSI at the outer, and then it's going to be the same sort of behavior all the way around that particular section. So again, the field of arrows which is, in my opinion, a terrific way of thinking about stress, because there's an arrow that exists everywhere on that cross-section. And in this case, it's tangent to the surface, it varies linearly from the radius, and it hits a peak at the outer value of the radius, which is, the value is 4.75 KSI. Our final step then is to figure out what is the angle of twist at C. Now this one's a little bit more complicated, because now remember that, I'll write this as theta at C, which is equal to theta of C relative to A, which is equal to theta of C relative to B, plus theta of B relative to A. Now we already know this one. This one is 0.00447 radians going this way. But now we realize that C relative to B, it's going to follow the torque. So already we know it's going to be this way. Now again, I don't care if you use plus or minus, but you have to realize that those two are not going to sum up. You're going to subtract one from the other. So let's get theta of C relative to B. That's going to be equal to the value of the torque. And again, I've already got the sign taken care of in that. So I can just put the value of 40. Then the L is 3 feet, which is 36 inches. It has a J, we already did this, but again, pi over 32 times 3.5 to the fourth. And then the value of G, and that was our 12,500. Plus, I'll say we've got the same value that we've got here. So we crank this thing out, and we do the numbers, and we find then that our value of theta of C is going to be 0.00335 radians, and that goes that way. So that must mean then that this segment must kind of dominate, because it's overwhelming the angle change that we got earlier. So that would be our final answer that we would write out. So again, use the double arrow, either to the left or the right, for our theta values. Don't say plus or minus. I don't know what that means. So we always want to go with that left or right double arrow. All right, that's a great FE style CIVE 360 exam type of example for basic torsion, and it closes us out for the third part of today.